All right, so starting things up, we're going to go over the homework from yesterday. These are pretty straightforward, so you shouldn't really have an issue with this, but I'll just go through it. So we have a 12-volt battery connected to a 6 ohm resistor. Calculate the current going through the resistor. Well, we have V equals IR is our equation, and we want the current. We have the voltage. Well, that's 12-volt battery equals the current I times the resistance of 6. So the current is therefore 12 divided by 6, so it's 2 amps. That's it. Like, it's really not, there you go. It's not really too much to go with that, but there you go. Pretty straightforward in terms of getting 2 amps there. Let's see, this one down here. Number 2, my laptop charger outputs 2.31 amps at 19.5 volts. How much resistance can the current cross that voltage? Okay, so here we have voltage, we have current, and we want to get resistance. So again, V equals IR. We have the voltage of 19.5 equals the current of 2.31, whoops, and times resistance. That's what we're solving for. So then to solve that, resistance would be 19.5 divided by 2.31, which is going to be, let me space this out to make it look a little bit nicer. Okay. Well, calculator this. 19.5 divided by 2.31. Okay, I'll round it to 8.44. There, you did the homework. Yeah, I told you that this stuff starts off very simple, okay? So, yeah, so that starts off very simple. But things are about to get a little bit more complicated. Your warm-up question now. So far, we've only talked about, again, just what do you do if you have one resistor? You have one battery, one resistor, what do you do? So now I'm saying, okay, now you add resistors. Okay, so you're going to add resistors to the circuit. What happens to the overall current? Okay, so think about, V equals IR. Your voltage. I'm assuming the voltage stays the same because let's say you have just one battery, the battery stays the same. But as you add resistors to a circuit, what's going to happen to the current? Okay, so give you a bit of time to think about this and see what you get. Okay, so hopefully you should have thought, well, if I add resistors, that means that my resistance number is going to increase, right? Because you add resistors to it. So if this number increases and this number stays the same, that would mean that the current would have to decrease. Except that's wrong. Well, okay. The answer is it depends. And how does it depend? It depends on how the resistors are connected. The current can decrease or it can increase. And this seems to not make any sense. You think, why the heck would it increase? I'm adding the whole point of a resistor is I'm adding things that use up energy, they use up current, right? So by adding more of them, I get more current, but you do, okay? And again, it depends how you do it. So this is why I said yesterday how this stuff gets very complicated. And that said, the basis of this is actually not so bad, okay? Even starting here, things are not super difficult. So I'm going to bring up the thing I showed you before, the lab thing here. You are going to be messing with this starting tomorrow. So let me actually kind of just put some things in place here. I'm going to now have multiple resistors. In fact, I'm going to put 3. Okay, I'm going to put in 3 resistors. So, 1, 2, 3. Whoop. 3. Okay. There's my 3 resistors. Now, can I? Oh, that's annoying. Yeah, I want it to be perfect square box. Whatever. So I have 3 resistors. Now, the question is, well, what is my current through this circuit? Now, of course, you could say, whoa, I wonder what the current is. Let me grab the thingy and figure it out. Oh, okay, it's 0.3. But the question is, how do you know that, right? What are you actually doing to figure this out? How do you get that number? And how do you actually, solve this without just, like, getting a measuring device? Or in other words, how does this measuring device actually even work? So in order to figure this out, we have to basically... we're going to still use Ohm's law, okay? So we're going to still come back to Ohm's law. So, works for all circuits. The question is, what do we use for R when there are multiple resistors? Okay? In other words, what is the total resistance of this? And your immediate thought is probably, well, in this example, 30? You're right, actually. So, how this works is if you have resistors all in a line, okay, so multiple resistors all connected in one line are said to be in series, okay? So a series circuit or resistors in series, that's when they're all in a line, okay? And how this works is that the total resistance for a series circuit is that the R total equals the first resistance plus the second resistance plus the third resistance, and you add just however many there are. That's it. So if you have three... That's not what I meant to do. 3 10-ohm resistors in series. The total resistance is 10 ohms plus 10 ohms plus 10 ohms is 30 ohms. Yeah, so that's very simple. And then if you want to go to, okay, how do I get the current? If these resistors are connected to a 9-volt battery, the current is can be solved using Ohm's law. So we have V equals IR, T, IR. So our voltage is a 9-volt battery. Equals our current times our total resistance of 30. So I equals, well, 9 divided by 30, which is 0.3 amps. So that's how we got that. Okay, and that's very straightforward. So logically, this also means that, let's say, here, wait, let me break that connection there, and let me add in a fourth one. So if I add in a fourth one here, what should my current be? Okay, well now, if I add a fourth one, my total resistance should be 40. Okay, so if I add a fourth resistor, my total resistance is now 40. I think I can get away with not directly calculating that. So my current should be, well, again, V equals IR, 290. So 9 equals I times 40. Therefore, I equals 9 divided by 40, which is 9 divided by 40, 0.225. Okay, so let's check with the thing. Is that what it is? I think this only goes to 2, so it should say 0.23 because it only goes to 2 decimal points. 0.22. Okay, I guess the 5 is. Why is the 5? Whatever. So anyway, I think you can agree that works. Okay, so this is pretty easy to understand, right? I don't think this is that difficult to kind of see how this is supposed to work. So let me kind of get rid of that one, and then let me disconnect a bunch of stuff here. And this one. Okay. So that seems pretty easy. That's pretty straightforward, and you could just keep going, right? I could add 30 10-ohm resistors. Therefore, my total resistance would be 300, I would solve the current, blah, 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 easy, easy, easy. Okay. Let me actually kind of snip all this out of the way, actually. Going to be into some tricksy stuff. All right, so now I'm going to do something different. I'm going to connect them in a different way. Because before, that was in series. That was when they're all in a line. Basically, there's one path the current can go through. The current had to go through all of those resistors. But now I'm going to do sort of the opposite. I'm going to connect this. I'm going to connect this here. Okay, so there's one. But now, there's that, and then I'm going to need 2 more wires. And there. So now, how does this work? Well, this is definitely different. So let's kind of see what situation we have here. We have 3 resistors still, but notice what the current does. The current, once it reaches here, it can either go this way or this way. And once it reaches here, it can go this way or this way. And then so basically in this case, whatever happens, the current is only going to go through one of these resistors, right? Before, it went through all of the resistors, but now it's only going to go through one of them. So, how do you solve for the total resistance here? Well, first of all, we need a name for this. So, when resistors are connected so that current only goes through one of them, this is what was the wording I used before? This is said to be, okay, is said to be in parallel. Okay, so resistors in parallel. Parallel is when they're all like this, where, and again, I could keep stretching this as far as I wanted to. Basically, I have a ton of different resistors, but I only go through each individual, well, electron, I guess, well, they're going the other way, but each individual electron is only going to go through one resistor. It's not, and also, it's not going to do some weird path where it's going to be like, oh, I'm going to go this way, and then go this way, and then go this. It doesn't do that. It goes through one, okay? Because it has to go through one of them. It's going to pick one and just go through it. Because generally with this, it's going to do, you know, sort of the simple option in this case. It's not going to do something crazy. So, how does this work here? So, the total resistance for a parallel circuit is, and this is the interesting part, 1 divided by R total equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. That's not a 3, that's a 3. Keep going. So here, let me, actually, you know, I'm gonna, here. Okay, well, whatever. So, it's again, so for series, you just add them. But for this, you add their inverse. So, let's get back to this example here. What is my total resistance number? Well, 1 over my total is 1 over R1. And again, it doesn't matter which one you pick, but this one is 10. Plus 1 over R2 plus 1 over R3. So, let me go back to this situation here. Yeah, okay. If you have 10 ohm resistors in parallel, the total resistance is this here. So therefore, it's 3/10. And you think, oh, okay, I'm done. But this is the thing you have to be very careful at. For in parallel, it's 1 over the total equals this. So in other words, 1 over the total equals 3/10. So therefore, the total is the inverse of 3/10, or 10/3, which is 3.33. Repeating. Okay, so that's something you have to be careful about. It's the how it's the inverse of your answer of adding up the. It's the inverse of the sum of the inverses. Okay, so you take each one as a fraction and you add them up to get an answer, and then you do the inverse of that number. Okay, so I added up these fractions, I get a fraction, and then do the inverse of that fraction to get the actual answer. So again, therefore, if these resistors were connected to a 9-volt battery, the current through the battery would be equals IR. So I have 9 equals I times 3.33. So I equals 9 divided by 3.33, which is 30? That seems too... no, not 30. Just solve it. Just hold that for a while. 2.7, okay. 2.7 amps. So, we can sort of check this now. And so here's where the interesting I said before. Again, the warm-up question, it depends on how you connect them. So, what happens to the current? So if I had one 9-volt battery and one 10-ohm resistor, okay, what's my current? Well, it'd be 9 volts equals the current times 10 ohms. That means my current is going to be 0.9. Okay, now in this example here, what did we get? The current was 0.3. Okay, so it was less. But in this example, instead of 0.9, it's 2.7. It's bigger. So, and let's check that. 2.7. Okay, so by connecting the resistors in parallel, I actually increase my current, which is super interesting. But that's actually what happens here. So you get something that's very interesting with that. Now, you can keep going with this sort of process, but we have to... Well, let's kind of stop and come back to this. Can I pick this up, this whole thing, and move it? Not really. That's annoying. Yeah, oh well. I guess here, I'll recreate the series one back over here, because I want to kind of get back to a series example. I want to have both of them here, because I want to show you some stuff with it. Okay, so far, we've gotten total resistance for series and parallel. That's fine. And we've also gotten a current number for both of those. Now, however, there is something that we have to be careful about. Oh, come on. Ugh, whatever. Okay. Okay, so those are both there. There's something to be careful about, and that is that what is that current number that we've been solving for? Okay. Ohm's law. So here I didn't specify, but here I did. I said the current through the battery would be this number. Okay, and that's what it is. The current through the battery. And the current through the battery, so I put it here, and we get 2.7. Now the question is that the current through the whole circuit? It's not. Okay, you'll see it's different. Here's 0.9. Here it's actually 1.8. Yeah, so it's different. And now, granted, we don't really usually care about, for example, the 1.8 current is only between these junctions. So this piece of wire right here and also this piece of wire right here is going to have a 1.8 amp current. That doesn't really matter. It's sort of like the current through one tiny piece of wire that's not doing anything. The current that we care about is we care about the current through the battery, and we care about the current through the resistors. Furthermore, we also care about what is the voltage that is used up to go through each resistor. Okay? So, because remember how this works, right? The current's always going through the circuit. What happens here is that the current, it basically gains voltage. Well, it really gains energy. We're just going to talk about like as voltage. It gains voltage by going through the battery. So any sort of current gets here, it's going to gain voltage. It's going to go plus 9. I have 9 extra volts. It's going to use up that voltage to travel through its resistors. So, and this doesn't really matter in this case here, but I could change all the values. So for example, let me have this one be 5. Oops. Let me have this one be 15. And let me do the same thing here. This one's going to go down to 5. And this one's going to go up to 15. Okay. So with these examples, let's kind of think about this, and here's what we want. So for circuits, we don't just want the current going through the battery. We want the current going through each resistor and the voltage used up going through each resistor. Okay, so this is where, how I kind of said about it being sort of like a math puzzle, this is where this sort of comes into play. So here's the rules. Here's the rules for how this works. There's rules for series, there's rules for parallel, and there's rules for when you do something even different from that. So here's the rules. For series circuits, and I'm making this kind of capitalized to show how this works. Here's the rules. So the rules that your total resistance is just the sum of your resistors. Your voltage, your current. Okay, so the current through the battery, which is I'm gonna refer to as I total. Okay, so when I say I total in this case, it's the current through the battery. That's what that means. That current, let's think about this. So the current that goes through the battery, where is it going to go? What is it actually going to go through? Well, it doesn't have any choice, right? It must go through each of these resistors. It has to. It has no other option. So the current through the battery must be the same as the current through this resistor, and this resistor. It must be the same. So the currents are equal. They're actually all equal. Then what about the voltages? And again, this is, in a sense, the voltage, how this is used up. So the voltage total, again, that's the voltage of the battery. Okay? In other words, think of it as, this is how much voltage I'm going to gain. Now, how much voltage am I going to lose going through the resistors? Well, here's the rule for this is that the total voltage as you go through the entire, as you're like an electron going through the entire circuit, must be 0. So I'm going to gain 9 volts by going through the battery. That means through the resistors I go through, I must lose 9 volts in total. Okay? So if I gain 9, I'm going to have to lose something, lose something, lose something. But in doing that, in total, it's going to equal a loss of 9. So my total voltage, the voltage gained by crossing the battery, must equal the sum of the individual voltages that you lose through the battery, or through the resistors. Now for parallel circuits, we have a couple different things. For one, the total resistance is different, right? It's the 1 over the total equals 1 over R1. Whoops, that's not a 1. Plus 1 over R2 plus 1 over R3. Okay, there's that. Now for the current, again, let's think back to this here. Now again, let's think about the current. My total current, that's going to be my current through the battery. Now, when I'm traveling along, once I get here, I have an option. I can go this way, or I can go this way. And then also when I get here, I can go this way, or I can go this way, and then I come back together. So here, my electrons that pass through this battery, some of them are going to go through this resistor, some of them are going to go through this resistor, and some of them are going to go through this resistor. But in total, and I don't know how much, right? If you may notice how this was a way of showing current, by the way, is that the speed of the arrows going through the thing is a way of kind of demonstrating current. So you can see, for example, the speed of these arrows is clearly faster than this arrows, which is faster than this arrows. So more current is going through this than this than this, but we don't know how much yet. We have to figure it out. But in other words, think of this as, again, think of it as like amount of water or something flowing through something. The amount of water that I have going through this part here, it's going to split, right? Some it's going to go this way, and some this way. But it's not like I lose water to the outside. I don't lose electrons to the outside universe. So sure, my electrons split, and some of them go through this resistor, some through this, some through this, but they're going to eventually come back together and going to stick back to this one here. So what's going to happen is that my total current, which is again my current through the battery, is going to equal now the sum of my currents going through each of my resistors. Okay, so for the series, the currents are equal. For parallel, it's a sum. Well, so then what about voltage? Well, again, remember what I said before, is that your total, if one electron going through the circuit must have a total voltage change of 0. So if I'm an electron, I go through my battery, I gain 9 volts, then I get here. Now, some of the electrons will just cross this resistor and then go back down and cross the battery. So that means they're going to gain 9 volts here. They're only going to cross this resistor, which means this resistor, when they cross it, they must lose 9 volts. But some of them are going to not do that. They're going to go this way, and they're going to go through this resistor. Well, they're still, once they go through this resistor, they're just going to then go back down and go through the battery again. So, and there's some that are going to go this way, but again, are only going to cross this resistor, then go back down again. So in other words, each electron is only going to cross one resistor, so they only have that one resistor to use up all of the voltage from the battery. So the voltage crossing each resistor is going to be equal to the voltage from the battery. So you can see the current and the voltage rules are different. They're reversed for series and for parallel. So let's actually use this example. So let's look at the first example where a series circuit connected to a 9-volt battery has a 5 ohm, 10 ohm, and 15 ohm resistor. Let me get rid of the A. Has ohm resistors. Okay. Find the current and voltage through each resistor. Okay. So we want to find what these are. So the first thing you have to do for any of this is to find the total resistance. That's the first rule for any of this. Now for this, that's pretty easy. Total resistance is just the sum of your resistors, because it's in series. So we have 5 plus 10 plus 15. I think you can all agree with me that that total resistance is 30. So our total resistance is 30. Now that we have total resistance, we can use Ohm's law to now solve for total current, okay? So we can still use Ohm's law, by the way. So for all of these, we can use Ohm's law for each individual point, as long as we're connecting things. So for example, V2, I2, and R2, those can be connected using Ohm's law. You can't connect V2 with I3 and R1, right? You can't do that, but you can connect these through Ohm's law. So we have the V total, because that's the voltage of the battery, and we just solved for R total, so now we can solve for I total, because V total equals I total times R total. So we have 9-volt battery equals I times 30. So I equals, we already did this. What was it? 0.3? I already forgot what it was. Was it 0.3? I don't even remember anymore. Well, here, we can figure it out. Yeah, okay. 0.3. So our total current is 0.3. Let me clarify that. Okay, so now we have R total, we have I total, we already had V total. So now, we can solve for the individual pieces here. Now, since we have I total, and this is in series, we know what the currents are for I1, I2, and I3, right? So, therefore, I1 equals 0.3 amps, I2 equals 0.3 amps, and I3 equals 0.3 amps. And we can, again, you can check this if you don't believe me. What's the current through this resistor? 0.3, 0.3, and 0.3. Okay, it's all the same. So the current is all the same through those resistors. So now, though, we need to know what is my voltage through each resistor. What is V1, V2, and V3? But now we have I1, we have R1, I2, R2, and I3 and R3. So we can use Ohm's law to solve for these voltages. So I1 is 0.3, and let's just go in order. Let's say R1 is 5 ohms. So let's say it's times 5. So V1 is therefore going to be 1.5 volts. Right? Yeah. V2 is going to be I2 times R2. So 0.3 times 10, so 3 volts. And V3 equals I3 times R3, so 0.3 amps times 15, so that's 4.5 volts. Now, remember, we have something we can now check is that, hey, my total voltage, which means my voltage through the battery, should equal my sums of my voltages. So V1 plus V2 plus V3 should equal the total voltage. Does it? 1.5 plus 4.5 is 6. 6 plus 3 is 9. Yes, it works. So, and again, we can check this. We can let's pull out the voltmeter here. Now this thing is kind of ridiculous looking. Basically, what you want to do is you want to put this at these spots here, and once you put it around the resistor, it'll tell you what the drop is. So basically, it's saying as between these two, as you go through this resistor between these 2 points, you lose 1.5 volts. Here, I think it's going to show negative just because I flipped the order around, but that doesn't matter. So here it shows 3, and here it should show 4.5. Yep, 4.5. So all of that works, okay? So we got the numbers for the series circuit. Now, we got to find it in parallel. Okay, so now let's do it in parallel. So a parallel circuit connected to a 9-volt battery has 5 ohm, 10 ohm, and 15 ohm resistors. Find the current and voltage through each resistor. Okay, so same exact process here. First thing you do, solve for total resistance. Okay, and we can do that. We have that here. So, if 1 over total resistance equals 1 over R1, which is going to be, because I have the same thing, yeah, 5, 10, 15. Okay, 1 over 5 plus 1 over 10 plus 1 over 15. Now, so for this, I mean, I could just without even really using a calculator here, just sort of figure it out. Well, 1/5 is 3/15, and 1/10 is oh, that's not a 15th, so I have to get the, okay, we'll have to do this to be 6/30. This is 3/30, and this is 2/30. There, just to keep this consistent here. It's sometimes nice just to deal with this just as like fractions and not mess with the decimals, but you know, so that's why I'm messing with this here. So this gets you 11/30. Because then once you have it this way, 1 over the total resistance is 11/30. Well, that means that my total resistance is 30/11, which is 2 point something. 2.7, okay. 2.727, we'll say. As my total resistance. Okay, so there's my total resistance. And now I have my total resistance, I have my total voltage. I can now again use Ohm's law to solve for total current. So voltage is 9. The again, we're solving for current, and the total resistance is 2.727. So, what is the total current then? The total current is going to be well, the inverse of this, which is, okay, 3.3. There's my total current. So now I have total current, total resistance, and total voltage. Now, since we're dealing with parallel, the voltage is equal for each of the resistors. Okay, so this means my voltage was an increase of 9. So this means as for each of these resistors, I should lose 9 volts across each resistor. So let's check this to make sure. 9 volts, go from here to here is a drop of 9 volts. Also a drop of 9 volts. Also a drop of 9 volts. So yeah, it all works in that case there. So my V total equals 9 volts, which means V1 equals 9 volts, V2 equals 9 volts, and V3 equals 9 volts. So now I have V1, V2, and V3. I have R1, R2, and R3. I can now solve using Ohm's law for I1, I2, and I3. So, we have V1 equals I1 times R1, which means that we have, again, V1 is 9 equals I1 times R1, which was 5. So I1 equals 9 divided by 5, which is 4.5. That's, wait, no, that's not right at all. It's not 4.5. Divided by 5. It's 9.8, right? Yeah, okay. What, did I say 9? What am I doing? 1.8, okay. 1.8 amps. Okay. Then V2 is I2 times R2. We have 9 equals I2 times 10. So I2 equals 9 divided by 10, which is 0.9 amps. And then V3 equals I3 times R3, and we have 9 equals I3 times 15, where I3 equals 15, so that's going to be 0.6. Yeah. Okay. And we can double check this because we know that the total current through the battery must equal the sum of the individual currents. So let's see. 1.8 plus 0.9 plus 0.6. 3.3. 3.3. It all works. And again, we can check with the lab. What is my current through this resistor? That was 1.8. Move this out of the way. This should be 0.9, and this is 0.6, right? Yep. So it all works. All of that works. Okay. Good. But we're not done. Oops. We're not done. Because here's the thing. I don't have to make a circuit that's just in series or just in parallel. I could do something like this. Hope I have enough wires to get this to work. They only give you a limited number of things for this lab. It's a little annoying. Kind of wish they'd let you go crazy, but oh well. I'm gonna want to do this. Yeah, what I want to see. This. Now this is not in series nor is it in parallel. It's both. Okay, you have sort of a piece of it that's in parallel, and this parallel piece is then in series with this one. So then what the heck do you do? Now, here, I'll change this one down to 5. And that one can stay 10. This one can go to 15. What the heck do we do now? Well, it's the same process, but what you have to do is you have to treat each piece like a piece of that type of circuit. So, for example, what is my total resistance? There's no easy answer because I have a series piece and a parallel piece. Now, this parallel piece, I can just solve right away, right? This is just a parallel piece I can solve. So what is my total resistance of this piece here? So let's see how this works. Oops. That wrap up out of the way. So we have a 9-volt battery is connected to a 5-ohm resistor that is in series with a parallel pair of a 10-ohm and 15. That's what the heck did I do? And 15-ohm resistor. Okay, so it's saying this 5-ohm is in series with this parallel piece. Okay, so find the current and voltage through each resistor. Okay, again, the first thing you have to do is find the total resistance, but there's no easy answer. So what do? You have to look at it piece by piece. The parallel piece is the easy part. Okay, this is the simple part. And again, you may think, oh, but isn't the 10 and the 5 in series? No, because of this connection here. So they're only in series when there's no sort of branch that kind of splits off in between them. Okay, there's this branch that sort of separates them. So that means you cannot count the 5 and the 10 in series. But you can count the 10 and the 15 in parallel, because if you sort of take this parallel piece, it's sort of exactly the same as sort of this piece here. So what I can solve for is my parallel piece is, well, it's the 1 over, right? 1 over the sum for the parallel is going to be 1 over 10 plus 1 over 15. This ends up being, well, again, this is your 3 over 30 plus your 2 over 30. So this equals, therefore, 5 over 30, which means my R parallel is going to be, well, not 5 over 30, it's going to be 30 over 5, which is just 6. So that means this parallel piece has an equivalent total resistance of 6. Right? Yeah, 6. So then, what is my total resistance? Well, that means these two together is like if I just had one 6-ohm resistor. Well, that one 6-ohm resistor is therefore then in series with the 5. So, my total resistance is just like treating these like they're in series. 11 ohms. That's my total resistance, 11 ohms. Therefore, my total current is going to be, well, here, I'll just put that down. Let's see, we have a voltage of 9. Current is I. Total times the total resistance of 11. So my total current is going to be 9 divided by 11, which is 0.81, repeating? Yeah. 0.818 amps. That's my total current. And we can check that using this here. Again, this is the current over the battery. Yeah, 0.818, 0.82, yeah. So that works. Okay, so that's good. So then the question is, okay, what the heck do I do to solve for the current and the voltage through each resistor? Well, let's treat this for what we know. Okay, we know that for resistors in series, the current's the same. And we know that for resistors in parallel, the voltage is the same. So let's think about this. Usually I think if we can pick out series pieces, that usually makes things a bit easier. So we know what the current is through this, through the battery, right? It's the 0.82, 0.818, whatever. Now, all of this current is going to go through here. It's going to split. Some of it's going to go through this, some of it's going to go through this, but all of it must go through this resistor, right? Because it comes back together. It all goes through this resistor, and then when it comes back here, it's going to all go through, right? All goes through the battery. So what this means is that all 0.818, of my current, it has to go through this resistor. So what this means is that since I1 is sort of a series piece of this, I total must equal I1, so I1 must equal 0.818. Let's check that. It does work. So then, what does this mean? This means for parallel. Okay, remember what we had for parallel. For the parallel pieces, the current is adding. So, we don't know what it is, but what we do know for the parallel pieces is that it's a sum. And we know that these two things must equal the total of 0.818. Okay, so whatever these currents are, when you add them together, they should equal 0.818. Okay, so then let's see what we have. We have I1. We have each of the individual resistors, and we have, do we have any voltages? No, we just have V1, right? Yes, we have, no, we don't have any of these. We just have the total voltage. Okay, so here, though, what do we have? We have no voltages, but we have I1, and we have R1. So this means we can use Ohm's law to solve for V1. So V1 is I1, 0.818, times the 5 ohm resistance. So, times 5, and we get 4.09. So our voltage for V1 is 4.09. Let's double check this. .09. Okay, so far so good. So, now, how do we keep going from this? Well, remember, the voltage is additive for series. So, we gain 9 volts here. We lose 4.09 volts crossing here. That means, again, the total voltage loss must be 0. Or the total voltage change must be 0. So, if we lose 4.09 and we gain 9 here, then when we cross this parallel piece, we must lose the rest of it, okay? Regardless of which one we go through. So, that means that V2 must equal V3, and it must equal the total voltage minus V1, which is 9 minus 4.09. So, V2 must equal, and then just, oh, right, okay. It's the not negative version of that, so it's 4.91 volts, which therefore must equal V3. 4.91 volts. And again, we can check this. So here, 4.91, 4.91. Okay, it works. So now, what else do we still need to get? We have I1 right here, and we have V1. That's this, and we have V2 and V3. So all that's left is I2 and I3. But we have V2, we have V3, and we have R2 and R3. So we can use again Ohm's law to calculate the current, I2 and I3. So V2 is 4.91 equals I2 times R2, which was 10, right? Yeah, 10. So I2 equals 4.91 divided by 10. Well, that's going to equal 0.491, not 499, 1 amps. And for 3, we get, again, 4.91, that's the same, equals I3 times 15. So 4.91 divided by 15, that's, I need a calculator for. I'll just do that for a while. Okay, divided by 15. Okay, 0.327. Now again, we can check this, okay? Because remember how the current works. For a piece in parallel, the current is summative. So this means that the current, these two currents added together, okay, the currents through these two added together should equal the current going through this piece, because again, the current, once it comes together, so this current plus this current, these two come together, they must in total go through this one, and also must in total go through this, so they should be the same, so once you add them. So, 0.491 plus 0.327, hey, 0.818, there's your I total, which is also your I1 right there. So yeah, it works out. So we have our numbers. We have all of our answers we need. We have V1, 4.09. We have V2. We have V3. And we have I1, I2, and I3. Those are our numbers. So hopefully you can kind of see why I said this is like a math puzzle, and how I kind of I don't know, I like this, even though it's like it's complicated, but like the numbers themselves are not really difficult, right? These are pretty simple numbers. I mean, some of the decimals are kind of gross, but like they're not like 10 to the negative rule or whatever. You don't have to worry about that. So that's nice. And the rules for this are simple. You're just basically adding and subtracting and multiplying and dividing, right? There's no crazy stuff you're doing, but it's this kind of like math logic-y puzzle thing that I don't know, I kind of like. But I think so. I don't know. There's some people like this stuff. Some people hate it. I guess you'll find out what we're going to do with this. So now, I want you to go for the wrap-up question here. A 2 ohm, a 4 ohm, and 8 ohm resistor are connected in a circuit. There are 5 possible combinations for these resistors. Calculate the total resistance for each configuration. Okay, so think about all the combinations this could be, and how this could work. Actually, I just realized something. This is actually a not correct way of thinking about it. There is actually there are more than 5 ways to actually connect these. Oh well. Okay, basically the ways that I'll kind of tell you what I was looking at when I wrote this. Basically, there's this way, and then there's this way. There's actually another way to connect this in a combination that doesn't look like this. But the things for this is that it depends on which resistor you put where, right? And so you can see how that works. So just think about how that would work and get some combinations going. So find it when they're all in series. This is just total resistance. You're not worrying about currents and voltages for the wrap up. So total resistance when they're in series, total resistance when they're all in parallel, and then total resistance when it looks like this. But for example, if this one could be 2 and 4 and 8, or this one could be 4 and this could be 2 and 8, or this could be 8 and this could be 4 and 2. Okay, so think about how that works in that sense there. And solve it and come back. Okay, so the simplest thing is to just, if they're in series, and that's just add them up together, right? 2 plus 4 plus 8, that's not a plus 8, and that gives you 14. Okay, so that's the simplest one. Second simplest one is if they're all in parallel. I keep hitting the backspace. Okay, so then it's 1 over 2 plus... No, I don't want that. 1 over 2 plus 1 over 4 plus 1 over 8. Okay, so then what do we get? Well, 1/2, 1 over 2, is 4/8, and 1 over 4 is 2/8. So if we sum that up there, we therefore get 7 over 8, which means 1 over our parallel is 7 over 8, which means, and our parallel, which I'll just simplify to RP just to make sure it fits, is going to be 8/7, which is 1.14 something. Here, you know what? I'll just screw it. Trying to be efficient in my spacing, but oh well. Which is, I'm lazy and just solve it this way. Okay, yeah. 0.4285. 7 ohms. And you definitely see a big difference here, right? So 14, 1.4, right? These are pretty extreme differences. So then, what are the other combinations? One combination is to have, again, as I said, it depends on which one you put in the parallel position and which one you put kind of by themselves. So one option is for if the parallel pieces are the 1 over 4. No, stop doing that. And the 1 over 8. Okay. If you do that, then you end up getting, well, 2/8. So then you get 3 over 8, which means the parallel piece. Hate the fact that it's right next to the backspace. I keep pressing it. Equals, therefore, 8/3, which is 2.667. And therefore, but again, these two being in parallel, this would be in series with the 2. So then you want to say my total is actually 2 plus 2.667. So it's 4.667. Another option is to do instead of the 4 and the 8 together, you have 1 over 2 plus. I really wish I could. I mean, I know there's a setting to disable that, but I'm lazy. So that would give you 1 over 2 plus 1 over 8. This gives you 4/8. This becomes 5/8, which means my oh, it's not even 1 over. It's 1. It's just R parallel. Equals 8 over 5, which is 1.6. So, therefore, my R total in this example, since I didn't use the 4, would be 4 plus 1.6. So I get 5.6 as my resistance that way. And the last method in that sort of configuration, it would be the parallel pieces are now, let's see, this was 1/4, 1/8, this is 1/2, 1/8. This would be 1/2 plus 1/4. Okay, there. I just caught it in time. So here, 1/2 is 2/4. So we get 3/4. So therefore, our parallel equals is 4/3, which is 1.333. Not 4.33, 1.333. So, therefore, I didn't use the 8th one, so it's going to be 8 plus 1.333, so we get 9.333. Okay, so there you go. Those are your answers. If they're all in series, you get 14. If they're all in parallel, you get this, which is 8/7. If the 4 and the 8 are in parallel, and the 2 is in series with them, then you get this. If the 2 and the 8 are in parallel and the 4 is in series, you get this. And if the 2 and the 4 are in parallel and the 8 is in series, you get this. Okay, so those are your kind of 5 examples how this works. There is actually other ways of combining these. And so think about, there actually are also, again, 3 other ways that I have not talked about here of combining these in their own way. So think about that. You don't have to put it in for the answer, but just think about it and see how you can get that to work. Your homework for this is actually something that I'm going to give you a lot of time to work on. Sort of this, and it's a worksheet on circuit stuff. And this worksheet, along with the lab that I'm going to go over tomorrow, basically think of these 2 things as like your spring break homework. Okay, so these 2 things, you're going to have all the spring break to work over them. It's not going to take the entire week to do so, but it could take a couple days. So that's what you're going for there. This stuff is kind of complicated and it's complicated, but like not because, again, the rules are simple, but how you apply them gets very complicated. So yeah, and you may notice on the final thing on the worksheet, there is a doozy of a problem, but I want to see if you can work it out and go through it. I will show you the answer for it later, but I want you to try it, okay? I want to see what you can do. It is tricky, okay? But I want to see if you can do it and pull things together and see what you can get. Okay, this video's gone on really damn long, so, but there's a lot to show here, but yeah, so tomorrow I'll show you the introduction to the lab stuff, and then you have all of spring break to work on, again, the lab and the worksheet that you have here. So, yeah, there you go. Okay, finally done for today.